I mentioned how logarithms were created to make complex functions simpler. Logarithmic differentiation pretty much does the same thing. It uses the properties of logarithms to make expressions simpler. And so, for example, let's say that you wanted to find f prime, and you had some mess of a function, like f of x equals like the fourth root of 2x plus 1 over like, I don't know, tangent squared x. Right, now you could do f prime, it's just the chain rule and the quotient rule, but it's simpler to use the properties of logarithms to simplify this thing. So, how you would do that, how you would use logs to simplify the expression is you would do this. You would first, instead of saying f of x equals, just say y equals, just easier to look at. And you would take the natural log of both sides. Which at first glance seems to make it more difficult, but then you use the properties of natural log on the right side. Because the right side is a mess, so we can use the properties of natural log to write this in a bit nicer form. So, we know that that fourth root can turn into a 1/4 in front, so 1/4 log. And then we have a quotient, which we can turn into a difference. Right, so we bring the 1/4 out in front and then break up the logs into two pieces. We can also bring this 2 down in front. So log y equals 1/4 log of 2x plus 1 minus 2 times the fourth log tan y, or tan x. And then now you differentiate. So before you do any calculus, you use logarithms to turn that complicated expression into a simpler expression. And then once that is done, you differentiate both sides. It's implicit because y is inside your function, so log of y is 1 over y dy dx. Right, just 1 over y, and then times the derivative of y. That's the chain rule. 1/4 log 2x plus 1 differentiates to 1/4 times the derivative of the inside function over the inside function, minus 1/2 log tan x differentiates to the derivative of the inside function over the inside function. And the last thing that we're going to do is we'll simplify this up a little bit, like the 1/4 and the 2 can turn into 1/2. But we want to solve for dy dx, the derivative, so we multiply both sides by y, because those two cancel out. And we get our answer. dy dx equals, parentheses, because the whole thing's times y. The 1/4 and the 2 give you this for your final version. Secant squared over tangent x. You can probably simplify that a whole bunch of ways, but I'm not going to. And then times y, we know that y equals this mess right here. Whenever you express an answer, you want to use as few variables as possible. So as we had our answer up here, we had the derivative in terms of x and y. But it's possible to express it just in terms of x since we know what y equals. And so we do that, and that's our answer. You could multiply this out and get a common denominator, but that's pretty much doing all of the work that we just saved ourselves. So this is where you would stop the answer. Almost always, if you do logarithmic differentiation, which is this, when you use logs to simplify and then differentiate, your answer is not the simplest answer. It's always kind of a mess. Now with this one, we could have done it without using logarithms, but sometimes you'll have a question like this. Let's say we want to find the normal line to y equals 2 to the x at the point 2 comma 4. So this function we can't differentiate yet. We don't have a rule for 2 raised to the x power. We know how to differentiate e to the x, but not 2 to the x. And so in this case, we have no choice but to use logarithms. We take the log of both sides. We use the properties of logs to simplify. We take this x out of the exponent. And now we differentiate. So first we use logs to simplify our expression, and then we differentiate once we have a form that is easier to work with. The problem here is that we had x in the exponent, which we could not handle with base 2. So we use logs and get the x direct down in front. We differentiate. Log y differentiates to 1 over y dy dx. X log 2 is just some constant, right? It's like 0.9 or something like that. So x log 2 just differentiates to log 2. Just like 6x differentiates to 6, or 25x differentiates to 25. X log 2 goes to log 2. And then multiply both sides by y to get your answer. dy dx equals log 2 times y, where y is 2 to the x. We could have, by the way, done that a different way. We could have done a change of base and then use the property of logs there. But either way, you have to use the property of logs to find the derivative. So now we have our derivative. We want the normal line at the point 2 comma 4. So to find the slope, we plug 2 into this expression. It gives us log 2 times 4, so 4 log 2. And then the normal line has a slope that is the negative reciprocal to that, since it's perpendicular. And so the normal line is y equals the y value plus the slope times x minus the x value. Oops, there it is. Okay, for a quick comprehension check, try this problem right here. Just find dy dx for y equals, I don't know, let's say sine x to the sine x power. So sine of x to the sine x power. So press pause until you've gotten the answer, and then when you're ready to see the answer, press play. So the issue here is that we have an exponent that isn't a nice exponent, right? If it was like sine of x to the 4th, then we're good to go. Just use the chain rule. But sine of x raised to a function of x, we don't have a rule for that. So since there's no rule for that, we have to use logarithms, because the logarithms enable us to simplify our expression. So again, if the exponent is a function, we only have a rule for that if e is the base. E to a function is no problem. But anything else raised to a power that is a function, you have to use logarithms to simplify. And so you would use logarithms, bring the power out in front, and now we're good to go. We can differentiate this. It's just implicit on the left and the product rule on the right. The derivative of cosine times log sine cosine. So it's just cosine times log sine plus sine times the derivative of log sine, which is the derivative of the inside over the inside. These cancel out, and we get cosine x log sine x plus cosine x. And then multiply both sides by y to solve for dy dx. And we get our final answer, dy dx equals cosine x log sine x plus cosine x times y, which is sine x to the sine x power. Some more space management issues I can't fit, but right here is sine x to the sine x power. And as is often the case, the answer is not very clean or pretty, but that's usually what you're going to get if it's logarithmic differentiation.